We're going to spend some time today talking about concavity again and the second derivative test. We have previously talked about the first derivative test, so this is the second derivative test. You'll see some similarities. But just to remind you, we had been talking about our graphs being concave up or concave down. It is concave up on this section here. You can see that that holds water, so concave up, and then this section here would be concave down. And the test for concavity comes from the second derivative. If the second derivative is positive, it's concave up. And if the second derivative is negative, that means it's concave down. And then we also talked about inflection points. Those are places where the concavity changes. And remember, these have to be actual points. If they're like asymptotes, if for some reason that point doesn't exist, it's not an inflection point. So just to remind ourselves of this, we're going to walk through this example here, number 3.5. We want to determine the inflection points and discuss the concavity of f of x equals x to the fourth. So to do that, we are going to find the second derivative. So the first derivative of x to the fourth is 4x cubed. And then the second derivative is 12x squared. To find those potential inflection points, we're going to take our second derivative and set it equal to 0. And when we solve that for x, of course, we get 0. So now we're going to come to the number line, and we're going to check on either side of 0. Now remember, we're checking the second derivative, so make sure you write that down so that way you're not confused about what you're plugging into and what you're checking for. So again, we're going to pick a number to the left of 0, maybe like -1. Remember, we're plugging it into the second derivative. When I plug in -1, I get a positive number. And when I plug in something on the other side, let's say I plug in 1, I'm also going to get a positive number. So this means that f of x is concave up on the entire interval, so -∞ to infinity, which we already knew that. Well, you guys know what the graph of f of x looks like, equals x to the fourth looks like. It's like a parabola. It's a little bit flatter at the bottom, so it kind of looks like this. And that is, of course, concave up on the entire thing. Now, I want to move into what's called the second derivative test. The second derivative test is for finding minimums and maximums. We previously in this chapter did the first derivative test. So to do the first derivative test, remember we found the first derivative and we found our critical points. Those were potential minimums and maximums. And we put our critical points, let's just say they were these, and we plugged into the first derivative and we decided where it was increasing and decreasing, and where it changed it. So if it changed from increasing to decreasing, we said this was a relative maximum. And if it changed from decreasing to increasing, this was a relative minimum, okay? That was the first derivative test, and we were finding minimums and maximums. So we're not doing the first derivative test anymore. We're doing something called the second derivative test, but it is still a way to find minimums and maximums. So what we're going to do is we are going to find those critical points again. The critical points are C, and we're going to plug the critical point C. Let me write that down. We're going to plug the critical points into the second derivative. If the second derivative is positive, that means it is concave up there. So that point C would be a relative minimum. If the second derivative is negative, that means it's concave down there, and that critical point is going to be a relative maximum. Now, if the second derivative is 0, then the test fails. Second derivative test doesn't work, so it might be a minimum, it might be a maximum, it might be neither. If that happens, we have to use the first derivative test. So we have to back up to what we had done previously. So let me walk you through an example of this. Maybe. Give it a scroll. There we go. So we want to find the relative extrema of this function. So what we're going to do first is find our critical numbers. So first derivative is negative 15x to the fourth plus 15x squared. I'm going to go ahead and factor out a negative 15. Doesn't really matter. Negative 15x squared, which is going to leave me with x squared minus 1. I could factor that some more, but I don't really need to. That means our critical numbers are 0, 1, and negative 1. Okay. If we were doing the first derivative test, then we would plot this on a number line and see where it's increasing and decreasing. We're not doing the first derivative test. We're doing the second derivative test. So now that we have these critical numbers, remember these are our potential minimums and maximums, now we're going to find the second derivative. So the second derivative is negative 60 x cubed plus 30x. And now we're going to plug in our critical numbers. Okay, so first I'm going to plug in 0. So I plug in 0 and I get 0 plus 0, which is just 0. So the test fails. So we'll come back to this one. We have a problem here. Let's try another one. Let's try negative 1. So if we plug in negative 1, we get a positive number for our first term. Oh, I should probably write down what it actually is. Plug in negative 1, I get 60 minus 30, which is 30. That is a positive number. So this means that at negative 1, this graph is concave up. So negative 1 is going to be a relative minimum. At negative 1 something. If you want to find the something, you have to go back to the original and plug it in. I think it turns out to be negative 2. All right. If we plug in the next one, 1, we get negative 60 plus 30, which is a negative number. So since the second derivative is negative, that means it's concave down there. So 1 has to be a relative maximum. I don't know if I have enough room to write this. So we have a relative max at 1, 2. Again, I got the y value just from plugging back in. Now, remember, at 0 it failed. The second derivative test failed. So to check that, we're going to have to go back and do the first derivative test. So come back over here, just like we did before. We're going to plot all of these points and plug into the first derivative, and we're going to see what's actually happening there. So remember, this is my first derivative. So if I plug in something like negative 2, I get a negative. If I plug in something like negative 1/2, I get positive. If I plug in positive 1/2, I get negative, and then I get a positive. And if I plug in something like 2, I get negative. Okay. So again, the first derivative test, you can see at negative 1, it changes from decreasing to increasing, but we already know that that's a relative minimum. What we're concerned about is this point 0, and it goes from increasing to increasing. So this is neither. So even though the second derivative test failed, 0 turns out to not be a relative minimum or maximum, and these are our two solutions. Okay. If you pull this up on Desmos, which I don't have Desmos ready, but I can tell you what it looks like, you'll see that this graph looks something like this, and then it levels out here, and then goes back down, I believe. Okay. So you have a relative minimum here, a relative maximum here, and this point turns out to be neither. So that is the second derivative test. You find your critical numbers, you plug those into the second derivative to determine concavity, and that concavity tells you if they are relative minimums or relative maximums.